So the extreme value theorem left us in kind of an interesting place. We've said, okay, if we're on a closed interval, yes, there is an absolute maximum and there is an absolute minimum, but we have no mechanics on how to find it. So that's where we want to figure out how to find them. And it's actually going to be easier for us to look at finding local extreme values first. Okay, so let's take a look from a graphical perspective. So imagine we have a function. I'm going to draw it in red here, and we want to draw it with a local maximum and a local min. Okay, so a nice maybe cubic function, something like this. Okay, and so then I can start identifying, okay, here at x1, I have my local min, which would be f of x1, and up here, this might be x2, and then I have my y value at f of x2. Okay, so if I think about this graphically, what do I notice occurring at the maxes and mins? Okay, and there's a hint, so what is the value of the derivative at each of these points? Well, if I look, I drew a little tangent line here. Isn't that slope of the tangent line 0? And so this would mean that f prime of x2 is equal to 0. Does the same thing happen at the minimum? Sure does. F prime of x2 is equal to 0. Okay, and so that actually gives us a nice way to start to recognize where local extreme values might occur. Again, we have no mechanics for absolute yet, but we'll get there. Okay, and the result is captured in the next theorem. In Fermat's theorem, so if f has a local extreme value, again, that's either local min or local max, at x is equal to c, so I should clarify that this is x is equal to c, and we know that the derivative exists, then the derivative is 0 at that extreme value. Okay, so that's interesting. Now, the only thing is that this the reverse is not necessarily true. If f prime at c is equal to 0, that doesn't necessarily mean it has a maximum or minimum. Okay, so what could happen is certainly we could see what we saw in the graph above. So we could have, you know, a max occurring, a min occurring. But the thing is, there's also this nice other case that we've seen in more of a traditional cubic. So in each of these cases, right, here we would have a max, here we would have a min, but then at this case, we don't have anything. So this would actually be called, we call this in mathematics a saddle point. Okay, so if we know the derivative is 0 at a particular point of the function, then we have either a max, a min, or a saddle point. Okay, so we need to be careful. Okay, but at least what Fermat's theorem does is it gives us a nice starting place. Okay, we can start to form procedures, and so when we find, if we were to differentiate a function, assuming the derivative exists, and then know that the derivative must be 0 for us to possibly have a critical value, then, well, all I have to do is take the derivative and set it equal to 0 and solve for x, and the values we get, those c values, we call those critical numbers. Okay, so just so we have a bit of language, so if we say find the critical numbers, we're going to set the derivative equal to 0 and solve. So in our first example, we would have, 3x squared plus 6x minus 24, and we would set this equal to 0 to find the critical numbers, factor, we'll actually divide everything by 3, x squared plus 2x minus 8 is equal to 0, and I can factor this, x plus 4, x minus 2 is equal to 0, so then I have x is equal to negative 4 and positive 2, and those are the two places where, and so these are going to be my critical numbers. Okay, I'm just going to abbreviate for time purposes, but what would happen in this function is at either x is equal to 2 or x is equal to negative 4, I would have a local min, a local max, or a saddle point. So I'd have to figure out which one of the three I have, but at least I know where to look on the graph. Okay, so I want you to try f and h and resume the video when you believe you have found those critical numbers where those maxes and mins may occur. And here we go. Okay, so you can follow the algebra through on your own. However, again, these are all the critical numbers, and just again, a reminder, these are the values at which we could have a maximum, a local maximum, local minimum, or a saddle point. Okay, so we're going to use this as a stepping stone and use this in as one tool in the next method we'll see on how to find all the critical value or all the extreme values.